Yeah, so I'm going to talk about like representation autoencoders. Again, like this is a great audience, so I want to be a little bit like technical here. So yeah, like I did some slides this morning. Again, sorry. Yeah, I was like talking about like some latest advancements in representation learning, how we use like self-supervised learning to help like multi-model large language model understanding, and how we can actually build better self-supervised learning models, right? Like representation really matters for understanding. I want to just like bring that up because I want to tell you like this is all deeply connected, right? Understanding and generation, this is kind of central topic for today. But I want to say like this is all kind of like converging into similar thing, and like today I'm gonna be focusing on like the generation part, but hopefully you'll see representation also matters even for generate tasks. So, we started by building this type of scalable architectures, like, diffusion transformers or, stochastic interpolation transformers. This is basically like scalable diffusion transformer architectures, and, like it's simpler, it's scalable, it runs very fast. But, many people especially in academia, they complain to me, right? In order to get like this really kind of like nice looking images, or if you really want to compete for state of the art, right? You need to train these models for very, very long, right? Like you need to train it for 7 million steps, right? And this actually takes weeks to train, and it's like very infeasible for many kind of academia resources. So one thing they were thinking is like, does it have to be this difficult, right? Is there like a different, like more like different way of training such kind of diffusion models that can be easier and faster? So we started by thinking about like the internal, not just thinking, but like probing into the internal representation of such diffusion transformers. So for example, we took like, SITXL model, and then we looked at a few things, right? Like first of all, we look at this semantic gap, right? Like this is essentially, taking out the intermediate feature from diffusion transformer they were trying for diffusion model, right? And then you evaluate this feature on ImageNet kind of classification tasks with the linear probing. And then you can see actually there's a very big gap between the diffusion learned features and the state-of-the-art kind of external self-supervised learning features, right? Like leading models like Dino V2, they can achieve like even 84 top-line accuracy. But your diffusion model it's not learning garbage, right? Like it's actually representation is pretty good, but it's like around 60%. There's like very big gap. And you can also do something to check like the alignment score to the the foundation models like the Dino V2G, right? You can see there's also a little bit non-zero alignment between the diffusion learned features and the Dino features, but it's also like much more like worse than like other SSL models versus like Dino model. Okay, and then I think this is like the plus C here is most interesting to me. So like during the course of training, you can see actually the model, right? Like without any kind of like imposed constraints or like losses, it tries to be be more and more aligned with the Dino representation, but like the process is like very slow. It seems like diffusion model is trying to build up like good representation, but it's like kind of struggling to in achieving that goal. This is why we are forming this hypothesis, right? Like even for general models, especially for diffusion models, they must establish a very strong representation before rendering to the final kind of pixel output. Okay, and our hypothesis is if you only have diffusion objective itself, this is not sufficient to achieve that goal. So this is why, like, I guess it's like 2 years ago, we started this exploration. We called it representation alignment. Again, this is kind of like a different architecture, but it's like really simple, right? On the right side, this is just like standard diffusion transformer architecture. We have like DIT, SIT blocks, and have like this, huge transformer as your denoising backbone. What you do is like you will take one intermediate feature and then add a projection layer using MLP. And then you just add one, I should call it deep supervision here. It's kind of like auxiliary regularization loss. That's, the goal is to make sure your internal representation is aligned, right? The distance between your internal learned diffusion representations is, close enough to a per-trend variable encoders. And then you backpropagate this alignment loss back to this early layers, early blocks in your diffusion transformer. Okay, so it's actually quite simple. But once you do this, I think it's like really interesting observations that we have, right? Like going back to the plot that we have shown before. So in plot A, you can see, oh, by adding this kind of deep supervision from external representation encoder, you have much better linear probing, right? Like although it's still like worse than the DynoV2 like itself, but at least now like the gap is much more smaller. And it gets like better alignment as well. This is no surprise because you are adding this additional kind of like regularization loss to encourage the model to have better alignment. And then you can also observe like this linear probing results, this semantic information is actually correlated with FID, which is the generation quality. So once we do this, this is like really, at least at that time, this is like super surprising to me because it's such a like simple change to your kind of diffusion model training process, right? Just like add one loss, and then you have like almost like 18 times faster diffusion training process. Right. So now, like with just the 400K iterations, you can get like pretty high quality, images. While in before you have like pretty much kind of scrambled image. Okay, so this is REPA. But when we build like DIT or we like start exploration in REPA, we always ignore one thing, and which to me is actually the elephant in the room. In latent diffusion models, we always have this thing called VAE model. People don't talk about it. Like for diffusion transformer, we say, oh, we have like, use a transformer to replace ConfNet for the diffusion model, but we never touch the latent modeling, VAEs, right? If you think about this, like tons of advancements in diffusion transformer across like many tasks, but the autoencoder is still like largely following the SD-VAE paradigm, which was proposed many years ago. So why this is a problem? People started noticing, like this is a elephant in the room because actually there are so many limitations of the SD-VAE model. First of all, like it's like really high compression rate, so it leads to like weak reconstruction quality. It's like really low capacity latence. It's only 4-dimensional. Right. Later on, like people try to expand this to like maybe 8 or 16, but never like goes beyond that. This really lacks kind of like semantics. It behaves like pixels, like showing here, right? So you can actually plot this 4-dimensional latence. You call it latence, but it's like slightly fancier pixels. You can plot this in the RGBA format. So it's like really not going too far away from the original pixel space. And also, like from the architecture perspective, the VAE architecture is such a kind of legacy design, right? This is a kind of like convolutional kind of UNet without like escape connection, but like this type of backbone. It's very large, very bloated. It's like very inefficient. Okay, so people figured out this is actually a problem, so they thought about like possible mitigations. So one of the most straightforward way of trying to solve the problem is to, let's say, inject semantics back to this kind of legacy SD-VAE architecture. So this work is very good. This is called like VAE. So what they did is like very similar to the REPA work that we just saying before. But in our case, we are doing this alignment in the diffusion, like early blocks of diffusion transformer. But in VAE, they have a separate stage where they do the representation alignment directly on SD-VAE models. Okay. There's like other type of work. We also have like one exploration. Similarly, we can still use like representation alignment loss, but this time we not only backpropagate the loss to the early stage of the transformer model in SIT. This time we can unlock the VAE model as well. So like we backpropagate this kind of semantic alignment loss all the way back to the VAE. So this actually helps the performance by quite a lot as well. So we talk about like all these, methods or solutions based on representation alignment, and they seem to be very effective, right? If you think about like all these methods considered together, we can have like maybe already like 40 or 50 times faster training compared to the original kind of DIT or SIT model. We achieve this by kind of injecting the semantic information to all this, either like the early blocks of the diffusion transformer or all the way back to VAE. A natural question then becomes, if representation matters, why not like get rid of the redundant injection step or alignment, stage, and directly diffuse the semantically rich variant encoders or variant representations, right? This is like a natural questions many people asked, and we started this exploration for a very long time ago, and actually. This is done by my student, like first year PhD student Boyang Zheng. He's actually here. Can you say hi to people? Yeah, yeah. So he's amazing. Like we have been working on this for more than a year. Partly just because Boyang is very like patient and persistent in fixing this. Like the other reason is like I think there's so many things that we don't understand. So we want to really try to find out like the principles behind all this, kind of empirical results, rather than just like showing like one result. So like this is actually extremely simple, right? So essentially, as I mentioned, the idea is basically directly denoising a semantically rich encoder. And this poses many advantages. First of all, like latent space with rich information. This can be, saying from this representation quality, right? In original SDVAE model, if you measure the representation quality using linear probing on ImageNet, only gives you like 8% of classification accuracy, right? While like, other models can achieve like, 84 or something like that. And then, of course, now like we can actually make this a real diffusion transformer because the VAE part is also like VIT blocks. This is like much more scalable, and compared to the original design, right? Like even with a VIT-B design, this is only kind of 22 G flops. We train a separate decoder is around like 100 G flops, but all things considered, this is like much smaller and much more efficient, autoencoder compared to what we had with this VAE legacy design. All right. So I think there's a couple questions. For example, when we want to train this RE model, the first question is how well can you do reconstruction? So again, like the training process of this RE model is like very simple, right? We phrase the pre-trained autoencoder E. This can be like maybe a Dino model or like cyclic model and MAE model. It's fine, like any external representations. And then what you need to do is you need to train a VIT decoder D for the reconstruction loss. Okay, so it's actually a rather complex but still like quite standard combination of L1, L pipes, and adversarial loss applied to D. So, like results are quite surprising to me at least, because, some common argument is if you're kind of external representation, when they were trained, they focused too much on abstract meanings and they lost the capability of, being able to reconstruct the fine-grained details. It turns out like, with Dino V2 and Cyclic B and especially MAE, right, like they can reconstruct images. So we have the RFID numbers here, actually, our SDVAE achieves RFID of 0.62, and then for Dino model and like Cyclic model and MAE model, they all perform like better than the original SDVAE model. So this is not it, right? Like we are not working on low-level vision, right? Like we don't. To be honest, we don't care about like reconstruction quality. The real problem is how well does it support diffusion? How well does it support like generation? So some paper call this diffusability, right? So, the first observation that we had is this does not work out of the box, right? This is why, like, Boyang was so persistent because, if you directly apply this idea, build this autoencoder, diffusion model doesn't work at all. So it performs like much worse than SDVAE. This is like direct comparison here. If you use RE model, you achieve like FID of around 200, but if you use SDVAE, only 50, right? Similarly for larger model, like SDVAE performs much, much better. The core reason or the core difference here is for RE model, it's really a high dimensional diffusion process, right? If you think about like RE latent, this RE latent dimension is basically the external representation kind of dimension, right? Here it's 16 by 16, which is like their, defined by their patch size. And then the channel dimension is 768. Again, compared to VAE latent, which is like very low dimensional, only 4 channels, right? So we kind of found out like this is a major difference that actually, breaks diffusion. And then we started exploring, why this is the case and is there any kind of possible fix? And we identify three main issues: suboptimal DIT design, suboptimal noise schedule, and also inherent small errors made by diffusion. Like all of this because like when we design original diffusion transformers, we always try to adapt to this latent, space that's characterized by the SDVAE model, right? So a lot of these kind of design decisions were for the low dimensional kind of like, latents from SDVAE. And now, like, if we have like a totally different latent space, we think like many things need to change. So the first thing is we must make sure DIT width D matches or exceed RE latent channel N. So I want to repeat this one more time because I think this is important. So there's like two dimensions. One is the DIT hidden dimension, like transformer width, which is D. We need to make sure this number matches or exceed the RE latent channel N, okay? So why this is the case, we have some theory, and we can have like develop like a theoretical lower bound for the training loss when D smaller than N. I'll skip this part, but we have like one interesting empirical kind of experiment here. So basically, like this time, we're not training a diffusion model for some complex distribution matching problem. We ask the diffusion model to only overfit one single sample, right? This is like such a trivial task, right? But if you can see, if your D, again, like the diffusion model kind of hidden dimension is smaller than your per token kind of like channel from your kind of like autoencoder, DIT completely fails to overfit. It only actually works when D, equals or larger than N, right? Sorry, like this is a little bit blocked, but this is regardless of the capacity of your network. So essentially, this is not just like simply a capacity problem. You need to make sure your DIT model is wide enough, right? If it's like not wide enough, you can kind of increase like depth to have like very big model with high flops. It still doesn't work at all. So again, we have like some analysis in our paper. I just want to give you like, one very high level description of what's going on, the intuition behind it. So, Judge already mentioned, right? Like for a lot of this data, like in real world, that actually follows a very low dimension, intrinsic dimension, right? So essentially, it may be like in many like other applications, it's fine to have like a narrow network, right? Like at least the dimension can be smaller than your raw kind of data dimension. It's fine. But in the diffusion process, you actually diffuse, like because you are adding noises to the data manifold, you actually make it a full rank matrix. So whatever you do, like if you have just like projection matrix, even in the beginning of your network, you lose information. And this is like not recoverable. So you always have like a big trouble, for this kind of diffusion process, diffusion training. So I think this is kind of like, very simple but very important observation. That means like, in order to make high dimensional diffusion work, you need to have a wide enough neural network. The second point is we must adapt the diffusion noise schedule to account for the channel dimensions. So this is also not new, right? Like, I believe like the first formal paper talking about this is from a King Chen's paper on the importance of noise scheduling for diffusion model. But, in SD3, they also did this. So essentially, they propose shifting noise schedule according to different input resolution, right? If your input resolution is H times W, you need to kind of adjust it, the noise schedule so that equal amount of noise are added across our resolutions. Again, some simple, intuition. This image is from Boyang. So essentially, if you look at like this cat, right? If you have like low resolution image here, you're just like adding the same, level of independent noise across different scales. You can clearly see, I hope you can clearly see, like if your image resolution is very large, right? So you can see clearly, like, the details of the cats and so on, right? That means like, less information is actually destroyed with the same level of independent noise if you can vary your input resolution. You have to kind of like adjust your noise schedule to account for that. Otherwise, in this case, your diffusion model is looking at like much simpler, task. If it's not challenging enough, you're not like learning, high quality kind of representations. So this is actually make a huge difference. So without this shift, your GFID is only 23. But with this shift, it can be like just the 4.8. Again, what we did is like very simple. Before, people only consider the resolution H times W, but now like we use kind of a similar kind of empirical rule, but like now we account for the factor of N, which is the number of channels. Okay, the final point is we need to make the decoder robust to small errors in diffusion sampling. So this is kind of one major difference between RE and SDVAE, because like VAE model is not deterministic, right? Its encoder predicts a latent mean and variance, and then you sample latent following this equation here, right? This actually make SDVAE decoder more robust, because even if like diffusion made a small error in the sampling, decoder would just like take it as a Gaussian noise in Z, because during training they are doing this kind of sampling procedure already. But on the other hand, like our previous recipe for RE decoder, it's basically a deterministic process, right? So, one simple kind of fix here is during the decoder training, we also add a very small amount of noise here, also sampled from a Gaussian distribution, to the latent Z before kind of fit this into the decoder training, right? This is like noise augmentation for decoder training, very simple. So similarly, this actually hurts the reconstruction performance. This is what I mean by like, we are not really working on reconstruction. We need to work on a proper kind of like, autoencoder that can support kind of generation, right? So in this case, your RFID becomes worse, but you have like actually better generation FID. Okay, so once we do all this, it's already better than RAPA. So again, like one of the motivation for us for RE is we don't want this external alignment losses, all this cumbersome process. We just want to diffuse the semantic meaningful encoder directly. So actually, after all these fixes, this is already much better. This is also like 16 times faster than the RAPA work. Okay, so this actually works. But we didn't stop here. We want to ask this question about scalability, right? Recap, like our model, our DIT model in this kind of recipe with RAE need to be wide enough. But if you think about this, this might not be sustainable to scale the model with RAE channels. Imagine like we didn't do this right now, but imagine in the future, our best kind of like RE model will be of channel like 4096. That means like your DIT will be huge, right? Your MLP dimension will be 4 times in this number. It will be like 16K. You don't want that. So one thing we can do, I would say this is kind of like workaround, is to use this specific kind of like construction called decoupled diffusion training. This is from another paper. So this is why we call it kind of DT hat. So it's very simple. It's just to say, let's keep the DIT model fixed. We don't change this part. We don't scale it. This is standard DIT XL model. Okay. And then on top of this, we add a very shallow and very wide DDT head. This is again like another 2-layer of transformer. And this part actually handles like the velocity prediction objective. And then your original DDT will output some like information features that will be used as a condition to this DDT head. Okay, so this is basically for efficient considerations. We can now have like a much wider neural network without really incurring intractable overhead. So once we do that, like this is we are really pushing towards state of the art. Like DIT DH, like again like with DDT hat scales much better. Again, like it's much better than the original DIT design compared to other methods. It's like also converge much faster. And like this lightweight DT hat add a little bit kind of like overhead in terms of like number of parameters, but not much, right? So if you compare models of similar size, this DITDH with RE model really outperforms like many other approaches. One thing I want to mention is at this kind of like performance regime, all this absolute kind of like FID numbers start becoming like less meaningful. But one thing I'm super interesting is like this conversion speed, right? So one really promising signal that we have observed is we can actually get like 3.7 FID at only 20 epoch of diffusion training, right, without CFT. This is kind of like unimaginable a couple of years ago. It really shows like once you have this strong representation foundation, diffusion model is like something simple, right? It's like it shouldn't be the model that does the heavy lifting. So again, we have this, numbers, all these big tables. Again, one thing I want to say is like, this number, some people said this is already better than if you compare the validation data set on ImageNet. If you calculate FID, like the so-called lower bound is like only 1.78 or something like that. But still, I think like this is a problem for the field. Like we really don't have good metrics. But I still feel like this number is very meaningful because it's still like good proxy to tell like whether your diffusion process can solve this complex distribution matching problem or not. Okay. So one thing I want to encourage people to think about is like, instead of like just pushing for state of the art, RE actually enables many different possibilities. This is like one very cool experiment Boyan did. So essentially, we can actually train the decoder to perform like a form of super sensing on the 256 latents by just increasing the decoder patch size from 1632. Right? Because right now our kind of like autoencoder and diffusion process, this is all kind of like decoupled, so you can do something like very creative. So essentially, if you do this, this results in like 4x less tokens, yet very competitive performance for high resolution generation. And this is some like visualizations, and then I think I can stop and leave some time for questions. So when I first see all this examples from Boyan, I was like, oh, did you actually make a bug? Like this doesn't look as good as like leading papers. But then I suddenly, if you zoom in and look at this, it's just because like our model produced really, really diverse images, right? Like, with typically like all the paper will show an image with high kind of like guidance. And you will always see like maybe this husky or like some parrots, whatever. Like maybe they will face left, face right, but like similar, right? Images. But this time, like it's very diverse. You can see like a baby here with this dog, and there's like human faces here. I don't know, like the dog can be of different color. They could be like at different locations. So it's like extremely diverse. We'll have one more example to show here. Yeah, like for all these turtle images, birds. Like to me, I think when I see it, I feel like this really looks like really similar to the ImageNet training examples, right? Which is the objective for this kind of like toyish setup, right? You are like learning using diffusion model to kind of fit to the ImageNet distribution. All right, so I think this is the final slide. I want to be a little bit more assertive here. I feel like RE really offers clear advantage and should be the new default for diffusion transformer training. Of course, there's like so much work to be done towards building truly unified modeling paradigm. By the way, like another motivation that we really enjoyed working with RE is because this is really pushing towards building truly unified modeling paradigm that can both understand and generate. Yeah, I think I'll stop here and maybe take some questions. Yes.
So you basically try to, when you train the autoencoding, you actually make sure that the feature, the encoder, directly to match the distribution of the Dino representation, right? That part.
For the first part, or
yeah,
yes.
So yeah, that's actually very quite clever and also understandable, right? Because the Dino already learned a very good representation, especially contrastive and so on, structure representation of the natural features.
Yes.
And you really actually leverage on that. Good. And but you do know that we actually have some work recently about the simplified dinos. I mean, we didn't scale up to the industrial scale, but at then I think it really is this pre-training. Once you get a structural representation of the natural images, then that can guide the diffusion, denoise, and encoding, decoding, right?
Yeah,
that's very, very powerful. Yeah, in a sense.
If you can I say a few words about this? Yeah, I think it's very good question, good point. Actually, one more I would say like one more important motivation for this work is before when we work on SSL like MAE, we're kind of flying in the dark, right? We have like this really indirect proxy into like evaluating the model, right? We test on ImageNet or like segmentation, but then like love this just based on trial and error, right? I think like in this new era, what we want to do is to say, oh, actually, diffusion model can be an evaluation task for the underlying representation, right? Similarly, for large language models, it can be also an evaluation task.
Absolutely, even not just the generation as the evaluation of the representation is that how easily it's generalizable and controllable.
That's right.
That's precisely test how the representation are actually structured.
Yes.
And that facilitate all kinds of conditional sampling and generation, how efficient it is,
Yes.
and how structured it is, how controllable and generalizable it is.
Yeah.
So that's actually, I think, quite exciting. I mean, separating learning some good representation in a really unsupervised way, it's actually quite important. But you can very hard to compare, right?
Yes.
From MAE, which one,
It's very hard. Yeah.
which one is better, but you can do some probing, right? It's always a little bit wishy-washy. But now, yes, you can see that through the controlled generation, and those are the very specific tasks. Then you can see the quality, the controllability, generalizability, right? That actually we resonate tomorrow with some of the controllability and realizability
Totally.
that Qing we're going to talk about.
Yes, we chatted a lot. I think there's also like a very strong connection to more theoretical, motivations.
Yeah, wonderful. Thank you very much.
Thank you.
Okay. I also have a question. So
Sure.
I think for the representation autoencoder, it's very inspiring result to show that the representation model can actually do well in reconstruction, and also diffusion model is able to model this high dimensional feature using proper training strategy and architecture. But I'm thinking from another perspective that why the current representation models require very high dimensional features. Like in the future, do you think it is possible for to have like lower dimensional feature that can enable both understanding and generation, and in the meantime, the dimension is much lower than the current feature dimension?
Yeah, great question. So I'll think about this question from like maybe more practical kind of like considerations. So I think you will always go for high dimensional latents. Because like right now, like maybe if you don't work on this field, like maybe we'll have like some confusion saying, oh, you have a higher dimensional latents. Does it like make your like network much more inefficient and higher kind of memory cost? But like whatever latent dimension you have, you'll project this back to the kind of like DIT hidden dimension in the first step. So this is like for RAE, this is barely like almost no overhead at all, right? So in this sense, like higher dimensional means you have like more possibility to recover whatever like information that's necessary for your downstream. I think you always want to, again, you don't want to go too far, but like I think keep some flexibility is really important.
Yeah, I really want to add this. Okay, guys, this is important.
Yes.
Don't ever be afraid of embed your data into high dimensional spaces. In fact, you might have a blessing of it. As long as the embedding in the high dimensional space, your low dimensional structure is structured, right? They're linearized. They're already. That's why Dino and other things.
Exactly.
So don't ever be afraid that you have your data. For example, if you have a data in the subspaces, right? Let's straight line or to a plane. You can embed it, lift it up to 10 million. And you always have power iteration to get back. Okay, 10 steps, you're back, right? The noise is easy. Once you have structured the low dimension, if the intrinsic dimension of the feature is low, and also the structure is linearized, then getting the back, through sparse representation and so on, that's exactly the blessing of dimensionality, right? It's a structured low dimensional distribution in the high dimensional space is as good as they're already in the low dimensional space. The problem with the former, if you early on reduce your data, push your data into a lower dimensional space, they actually make them nonlinear. Actually lose information. It's very hard to actually compress. It's very hard to decode the information. So this is a very important lesson, right? We learned from high dimensional statistical geometry. Structured low dimensional, it's better embedded in the high dimensional spaces. Computationally, there's very little overhead to do that. In fact, I think that's what a hard brain is doing, right? We even introduce redundancy in our representation to preserve important low dimensional structured representations. The question is, once you get it, where embedded, then the diffusion compression is extremely efficient. Of course, if you have Saining, right, he will tell you how to engineer it very efficiently, right? But at least conceptually, it's doable. But how to really find it? It requires a little bit of engineering to get those diffusion operators, denoising operators, implemented correctly, right? So conceptually, this is an important mental picture. I think everybody should really be aware.
Yeah, I completely agree. I think one thing Boyan did is like he's really fearless. A lot of concurrent work were afraid, like, you cannot really go to high dimensional space, but I think we should talk more. Yeah, I agree with everything said.
Okay, thank you. Any other questions? Oh, yeah, you can use the mic.
Yeah, thanks for the great talk. I actually have a sense that your previous work, the RAPA, is kind of doing a distillation of the diffusion transformer to learn
Sure.
from the representation of
Yes.
the vision encoder. So I have what do you feel about the process? Say, measure the difference of DIT versus versus the normal vision encoder like Dino. Can we possibly like initialize the diffusion transformer with a representation learning encoder, or will that
I
be
thought this is what we
possible?
are doing here. No? I think RE is basically following this motivation, exactly this motivation.
Yeah,
right?
but you know that the DIT is still trained from scratch, right? Can we
Oh, I see, I
initialize the
see.
DIT with, for example, Dino?
Yeah, so like right now, this is still like not end to end. You have like two-stage training of like autoencoder and diffusion transformer. But I would say like, once you bridge this architectural gap, right? Now it's just like basically a huge kind of transformer, right? And then you can top like other, options where like maybe you want to make things like more closer to each other. That's all doable. Yeah.
Supervised learning, the feature space is already very high. So that's why you want to get the structural representation is already in the high dimensional spaces, right? So you're basically you're leveraging on that prior you learn. You try to match when you do diffusion, right? So the Dino tells you already gave you where the sort of located in that high dimensional space where Rome is. The diffusion denoise is try to build the maps from those two to actually get a decoder to leverage on that structure to do, right? I don't know. I mean, with the diffusion original variational encoders, it's also try to sparsify a little bit. It's try to do a little bit both, right? If you look at the VAE, it's actually the prior, the posterior, it's trying to promoting the features a bit sparse, but the space is too low. It doesn't really span it enough, right?
Not enough. Yeah.
And they sort of intertwine, getting hold of the distribution and also structuralize it together. So you just try to do a harder problem. You're actually combining two things together. Try to have so that's why maybe training the diffusion model from scratch with the original stability diffusion is a little bit harder. And let alone the VA is very hard to explain what the heck it's doing. Right now, you just get rid of it. You use the pre-trained distribution as a guidance, and you just do encoding decoding to guide the encoding decoding, right? Diffusion denoise and process. So, given that you learn the distribution is good enough, right?
Yeah.
Anyway.
So only one quick final maybe summary. I feel like one thing that we want to encourage people to do, you need to think about like representation learning and diffusion process, co-design kind of like, fashion. These are not like two separate processes. When you think about diffusion, think about generation, you really need to pay attention to the underlying representation as well.